organizer for inviting me for this workshop. I always loved the Wolfgang, but that's now this is a new experience, and it's good to see everybody online here. Hopefully everybody's doing well. Anyway, today, I understand today the workshop is about a non-standard finite element. So I'm going to talk about some non-standard finite element. And I'll begin with the motivation of solving high order PDEs. We're talking about 2m's order in RD dimension. You're talking about how do you do finite element for this high order PD. This is some kind of a topic which I'm obsessed with in the last few years, maybe 10 some years. And you look at the, m equal to 1 is Laplace, and then m equal to 2 is biharmonic. My question is that how to construct conforming finite element space in general for such a high order PDEs. And the answer to this question is still mostly unknown. It's still open questions. There's an open question how to construct conforming finite element spaces for arbitrary dimension, arbitrary M. I have to say this is more a mathematical exercise. Even though in practice you have high order PDE to solve, like fourth order in 2D for the plate. 3D, you do material science, phase field model, for example. If you do you do a regularization, you can do 6th order, 8th order. Anyway, but despite those applications, but for me, it's mostly by curiosity. How can I construct a finite element to deal with this case? But again, let me just reiterate that it is unknown how to do that. Actually, several years back, when I have Wolfgang in approximation theory workshop, I was asking this question. Somebody gave me a reference, and it had an answer, but it turns out that reference the proof has a gap. So it's still, as far as I know, it's still open. You have the, for example, Algirus, and everybody will know here. You look at some ref. This is just some sample of reference, okay? And Hu Jun and Shang You, I think, wrote some paper recently. I see Johnny Gosman and Michael Linian.
I don't know what that means.
I'm sorry.
If you like, I can search the web for.
I'm sorry, my iPad is talking to itself. I'm sorry. I don't know how I'm going to do it.
AI, right?
I don't know. Sorry about that. Maybe that reflects your guys' opinion. I don't know what I'm talking about. Okay, never mind. So I couldn't do it. I do the non-conforming method. So non-conforming method. When I say non-conforming, these days a lot of people do DG. Non-conforming, I call it like a DG without parameters. Okay, this is what I call non-conforming. Okay, you have to have some smoothness, but not much, I guess. If you do DG, I worked on this on and off for about 10 years, actually. I finally completed this project in some sense. Let me just go do this one. For example, if you do biharmonic, you do quadratic, this is a Morley element. This is what I call the most peculiar element in finite element every time I teach it. So it's discontinuous, not even in H1, but it works for fourth order problem. It doesn't work for second order problem. It's kind of strange. So I managed to generalize this and to all the dimension if M is less equal to D. So my colleague, from Peking University, and Professor Wang Min, so it's been a while. I didn't know how to do this M greater than D. M greater than D, for example, you will take a 6th order PDE in 2D if you care to solve it. So okay, here's the deal. Okay, I want to do the minimal order if you do a second order, you have to at least a second or a fourth order equation, you have to at least a second order second order polynomials. If you do a sixth order PDE, you need at least a third order polynomial. And again, for a while, I couldn't do it. Recently, I did this with my former postdoc, now he's a professor in Peking University, Sholan. And we use this the interior. I actually said that earlier. Sorry, we're not supposed to have any parameters or any extra stabilization. Now it turns out you need some stabilization term. I deliberately removed this parameter in front of it. I told you it's a parameter free, but it's probably a good idea to put some parameter there to adjust the balances two terms. But what I called, maybe a DG with minimal possible of stabilization. You actually have a DG, for example, in the old days, I have lots of DG methods. For example, I think Susan, Brennan, and many other people also did this kind of stuff. You can, but this one is just the lowest order polynomial with the smallest possible stabilization. I think but anyway, it's the lowest order means, I guess I'm done with this project. It's a non-conforming method. Now, the question is that what about conforming? We still don't know how to do. Now I'm going to take a non-standard finite element. Anyway, so I probably should summarize this a little bit. Anyway, it's a universal construction. Okay, one of the things philosophically, the most peculiar element becomes the most natural to me right now. Molly element, the way I see it from my theory, is the most natural element, one of the most natural elements to think of. Anyway, this is some papers. Now we're talking about non-standard finite elements. This is something that is by neural network. So here's the deal. So I take this what's called ReLU. For those of you who play with machine learning these days, ReLU is a piecewise linear function. It's a finite element function. When x is less than 0 is 0, x greater than 0 is x. So I'm gonna raise the ReLU to the power k. So so it becomes a piecewise polynomial for degree k in the following grid. If you look at the things here, it's a piecewise polynomial. Look at this. This one is a linear function, okay? You multi-dimension. You raise the power k, is still polynomial. But the discontinuous part, the element boundary is the level set of this linear functions. That is going to be hyperplane. So in 2D, you have this very special looking of grid. Okay, that fit the bill. Okay, it's a piecewise polynomial and for degree k, but it is conforming. So the construction is totally trivial. Now the question is, can we actually use this to solve my high order PDEs? Now let's look at the optimization, approximation theorem. These are the things which I spent quite a bit of time recently working on this stuff. And it turns out if k greater equal to m, you can get, if you, for those of the machine learning, you usually get n to the negative half result. N is the number of terms here, n is the number of terms here. And you can actually gain a little bit like 1 over d here. D is the dimension. Actually, this is something the best result we could get last year. But in the last couple of months, I worked with my postdoc, Jonathan Segal. And we proved the following kind of, for me, that is an amazing result for me. You can actually prove the best approximation is n to the m minus k plus 1. If you take m equal to 0, for example, you get k plus 1. It's a kind of independent of dimension. I'm going to come back to this estimate a little bit later on, but so it's a theoretical result. It's like if you think about that, maybe in finite general, you do interpolation, right? You do that kind of stuff. But in the machine learning business, to prove results like this, you do kind of sampling, which I'm going to try to illustrate that a little bit. It turns out the proof of this is highly technical. This is at least the proof we know right for now. I'm sorry, what is this thing? Is very technical to prove this thing. And let me see, let's just try to apply this PDE in any dimension. We do the Neumann boundary condition here. Detailed boundary condition, there are some issues. We can use Nietzsche trick and all that to get some estimate, but which because of the lack of time, I'm not going to get into this. So the way to do this business, we do a variational problem. Is, we cast this PDS minimization problem. Because of the Neumann boundary condition, I don't have boundary condition in the spaces. You do this. Now you can generalize this, what I call maybe neural network finite element, or in my paper I call a finite neuron method. You do the minimization, okay? In finite element, in the tradition, the standard finite element, this become a variational. You can do test the trial function, but this is a minimization problem. You don't have the other analogy. But now the question is that you can prove this one has a existence, but we don't know if it's unique. But it's non-convex, all that kind of issues. Okay, but when we'll come back to that later. Now the question: can we provide an error estimate? It turns out, actually, I actually didn't even expect that before. It turns out you still have the best approximation. It's actually pretty easy to prove. I mean, I didn't have the courage to prove for a long time, but once I decided to sit down to prove, it just takes a few lines. You have the best approximation, then you have these things here. So I have a piecewise polynomial of degree k, all right? For any partial differential equation of any order in any dimension with this error estimates. Okay, let's take some example. It's biharmonic. If a biharmonic, if you do Morley, okay, I don't have elements here. I have this what I call parameters, number of neurons. So another just to compare is that you think about number of coefficients in finite element. Here you have neurons. So you know in 2D, h is like n to the negative half, right? If you do the Morley element. If you do the to this one here, I have h square in something. It's n to the -1 if you think about this neural network of finite element. It's you square the things. If you do the algorithm, you do the n to the 4th. Is that right? Did I get it right? 5th order. Anyway, so you get n -2. But if you do this one here, you get n h to the 8th, n to the -4. I think there's some logarithm missing here. But anyway, as you can see, the rate of conversion is just so much higher. Well, you have the question about the sparsity, convex, all the other stuff. But it's not a fair comparison. But that's the comparison in terms of number of degree of freedoms involved in the finite element spaces. It's much higher. So I played this with this for the last pretty much year or so, and actually a couple of years. And again, only until recently, I worked with my postdoc, Jonathan Siegel. We just able to prove this kind of error estimate. I'm going to just try to give some introduction about some description about how we get here. And let's begin with some. Let's look at finite element. Everybody knows this is our finite element. That's our standard finite element. But I'm going to start from here So this is our basis function, you know, this is our basis function. This is basis, if you do a uniform grid, all the other nodal bases do a translation and a dilation, okay? And if you do that, so basically this finite element space would be a dilation, it's going to be a span by the dilation translation of this guy here. But it's not easy, difficult to see that this kind of height function here can be written as a combination of this ReLU, which I showed you 0x. So this phi I would be in the span of this ReLU here. And so the finite element is a very special, it's contained in the neural network, and with this height function, the activation of the ReLU. So if you make this WHBI arbitrary, if you look at the finite element, this W is very special. W is 1/2H. BI is this guy here. But if you make them arbitrary, that's what we call neural network. Okay, this is what this machine learning people do. I actually like to call that neural network is just a finite element method. Well, let's see, what is this? So U of n is, this is just a, you know, you can write this, if you take a K, you know, this function will be expressed this in differently. You have different ways like that. And so one hidden layer, this is what called one hidden layer. You can call this activation functions. You have n neurons and all that. Now you can generate the multi-dimension is totally trivial. You can just replace these things by linear function multi-dimension. Okay, just put that one in there. And then you all of a sudden you get a piecewise linear function in multi-dimension. But you can actually, you can raise the power k here in this guy here. You get a piecewise polynomial of degree k, we call this one here. Okay, this is 1D, but the multi-D you can get, so you get a subspace of HK and the HM if k is greater equal to n. You have a piecewise polynomial, which is looked like this, okay? So you think of piecewise polynomial of degree k, it's a finite element, okay? But it's the grid is very, very special. You know, if you think about what is the boundary? The boundary is this continuous point of this guy here. Namely, is the level set of is the WJX plus BJ, 0 level set of that guy, which is the hyperplanes. So you imagine yourself, your multi-dimension, you have a hyperplane that cut it through each other. Then you have this crazy looking grid there. That's my finite element grid. Well, you can also replace this if you play B-spline. This is a ReLU. I actually, somehow everybody in the machine learning likes the ReLU. Based on my recent study, somehow I don't find the ReLU is really a great function. But anyway, if in this case you ReLU K, you can think about B-splines. B-spline, you have this height function like this one. B1 is my height function. You can do B-spline, you can actually can relate this ReLU to the K-spot by B-spline of order K. So now we're going to ask of this approximation property of this neural network. So this is so we actually did this ReLU, but you can actually put any sigma there. Okay. So if this is the, you know, the neural network, sorry, my notation in my slides may be not very consistent because I was pulling slides from different places. But anyway, you have this sigma here, and it's any one-dimensional function. One of the first questions machine learning people would ask is that what kind of sigma that makes this functional class to be rich, so you know, it can approximate anything basically. And so this has been well studied in the literature. For example, usually we like polynomials, and we all like polynomial or piecewise polynomial. But the interesting question is that the answer to this question is that if sigma is a polynomial, you cannot do it. Because sigma polynomial fixed degree is always the same degree. So polynomial, one of the interesting results in machine learning is that as long as sigma is not a polynomial, you always go to function, get a good function class. And well, it has to be a function of some sort. I think the one of the sufficient conditions, if sigma is Riemann integrable, then you can generate the very rich functional class. But in our case is that we're going to do this is special. I'm going to look at a special one. I call a cosine neural network. The cosine network is that I'm going to take sigma to be cosine functions. You may ask me why I want to do cosine for two reasons. Cosine is the easiest functional class to analyze. And secondly, it is the neural network function that help us to analyze this reduced to the case power. So for those of you who have not seen the machine learning kind of, I'm going to walk you through how do you do the analysis of a cosine neural network. And so usually, you know, when you actually, usually when in this business, in machine learning, there's lots of probability language. I don't want to use any probability, but I still call it expectation. Expectation is just the integral, okay? But you have this probability density here. Basically, if this one is equal to 1, this integral equal to 1. That's all to it. But if you have this one-dimensional things, so I'm going to do a multi-dimensional. This is my E of G. If you do multi-dimensional, they call it independent variable. I'm going to call it independent also variable in the calculus sense. So one of the magic identity I would call is a very trivial identity. Is the following. Is the if you take this one-dimensional expectation, take the average of it, then you take omega as the independent variable, what they call sampling, independent sampling. Then you take an n-dimensional expectation. You can see that this is an identity. You know, so then if you want to do Monte Carlo method, that kind of, it all comes from here. And this is a trivial calculus identity. I wouldn't call it anything statistical or anything, probability. It's a calculus identity of multivariable functions. So, you know, for those of you, if you want to play with this machine learning, I would suggest you start from here. So now let's do this cosine business here. So we're going to use Fourier transform. This is the inversion. I do the inversion formula. So I'm going to rewrite, take the real part. If U is real, I take the real part. This I write this U hat as the real part with this some kind of write this formula. Then become a cosine. Okay. And you put this L1, this is what I call a probability distribution because the integration is equal to 1. So you can return this U of X as the integral representation, okay? And so Monte Carlo sampling. So basically, I'm going to choose this, WI to be independent. Okay, I plug that one in there. So you can be written as this one, you plug that one in there. So U of Ux minus UNX is equal to that guy. Okay, that's by definition. Now now by this identity which I showed you earlier, what do they call, what I call lemma 1. So you take the expectation, then you take the nth dimensional integral is bounded by that. Now I'm going to take the integral with respect to x on both sides, okay? Then I get this u. I typically write the omega n because this un is this guy, okay? It depends on x omega 1 omega n. when you do the integration, is with respect to the E of n. You integrate with this guy with probability measure. So you just say, you know, if this whole integral is less than or equal to this guy, there must be at least one point should be less than Geiger. That's the end of the proof. Okay, this U of n is equal to that guy. The G is a cosine. So you can pretty much say you have this cosine function that you prove the existence of the cosine network. You have this n to the negative half. This is what I call a sampling argument, but for me, I don't do any sampling here. It's just a calculus. Okay. But now, that's the n to the negative half result. Recently, I just want to see, can you do better for cosine? As it turns out, if you have a cosine network, which this is something I did, wait a minute, do I have reference here? This is Jonathan Siegel. Why did, you know, I'm trying to get Jonathan to add his reference here. Jonathan Siegel, my postdoc, he did most of this analysis here. And if you do this something in a unit cube, you want to extend this out a little bit, you cut it out down. You can make it a periodic extension, for example. You can pretty much write this as a Fourier series on this some kind of scaled lattice, like this lattice. And it turns out if you do for those of you who have played with this n-term approximation, nonlinear approximation method, this is orthogonal expansion, okay, in that lattice. You can pick the largest coefficients, you know, n-term with some weights. That's the approximation. If you do that, you can prove the following estimate. Yeah, okay, this is the paper Jonathan and it's already in the archive. And you can prove, this is interesting. Do I have this H? Oh, yeah, this is what the BS norm. This I'm sorry, this is probably doesn't sound so good, BS, but it's a Baryon norm with this S order. And you know, this is the, you know, it's a Fourier method. If you think about Sobolev space, you have a square there, okay? But the Baryon space doesn't have a square. This is L1, which is some weights there. You do the extension of that. And if you do these things, you can prove the following things. If the U is smooth, this S can be anything, okay? So you can get this is like a spectral, this is like a spectral accuracy, okay? The cosine is like a Fourier method. You can get as high as you wish. We actually have an exponential convergence result, but I think there's a Petroshev, classical approximation guy. He did this for some kind of Sobolev space, which is kind of a smaller space than this one, roughly speaking. And but we did there's a Baryon space. So that's the preparation. We also proved that this approximation rate is actually sharp. And with this regularity, you can prove a lower bound. We'll come back to it later. The way to prove, now the next thing is that maybe we should have some more details. This is related to the case here. This is the one we did this one here. Let me just summarize this. For the cosine network, you can get as high as you wish, as long as you have enough regularity. This is like the polynomial, or maybe, and it's not surprising, but we managed to present in the correct setup using this Baryon, we call it spectrum Baryon space. Now we go to the reduce the case network. I'm talking about this piecewise polynomial degree k, okay, reduce case power. So the way to do this business is that you can write this like a Fourier series like that in this kind of a shrink, the scaled lattice, and the scaled and shift lattice. And then you approximate this this particular function, 2 pi I, this function. It's a one-dimensional, it's a very smooth function by a multi-grid expansion, by a multi-grid, using the B-spline to do the multi-grid. Actually, amazingly, that in many of these analyses, for the friends here who know me, the background is that mostly my career I've been working on multi-grid method, but you know, this analysis, there's lots of multi-grid analysis actually. This is one of them. If you do the things that, there's lots of technical stuff here, you can actually prove that the best approximation with the HM can be written as end of the MK plus 1. Again, the proof is in a paper in the archive. Even though the proof can be probably be simplified, but anyway, that's the. Okay, let me just try to. Anyway, I just want to make the comments that I'm going to come back to later. If you think about it in terms of a finite element, this one is this norm the coefficient may depend on dimension, but this rate of convergence does not depend on the dimension. This is one of those things where many people working on machine learning say, wow, the neural network has this wonderful thing which has no curse of dimensionality. That statement is kind of can be subtle to make it precise. But one of the things here, indeed for this convergence estimate, you don't have the D. Usually you have to divide it by D here. And it's actually a shallow neural network. We don't even do deep neural network. It's just one hidden layer. And we can also prove this rate is actually optimal up to a logarithm. It's a logarithm, we don't know how to get rid of them yet. And okay, we can also prove this one's a lower bound. Actually, you cannot do better than the if U is actually not a piecewise polynomial, you cannot do better. This is the lower bound. Somehow for finite element method, we don't usually talk about lower bound. I don't know. We actually used this some years ago. I think who are in the audience here, but I think I was talking to Fu Jun many years ago. They're doing this. They use some lower bound for the eigenvalue analysis. So I was actually I got curious about that. We wrote a paper. I wrote a paper with Professor Lin Chun and Xiao Hu. We did the lower bound. I was actually surprised that we could not find any literature about the lower bound of finite element. Here's the lower bound. Let me just explain to you. Maybe after this meeting, somebody can tell me, maybe there's some reference. This is already 6 or 7 years ago we published the paper. And let me explain the lower bound here. But again, the reason I will do a lower bound, and in the machine learning, especially statistics, they always like to do lower bound for some good reasons. But here, I'm just happy. This is again related to what I did, a few years ago. If this U itself is not really a piecewise polynomial, it's not in the space. If it's in the space, you have no lower bound. Okay, it should be smooth. But I might want to emphasize that here, I don't have this adaptivity business here going on. I have a very smooth function, okay? So quasi-uniform grid are pretty much more or less the optimal grid. I don't have singularity here and there. I actually find the neural network is probably very good for adaptivity. That's probably a different topic. It's not something I'm going to emphasize today. And you can actually prove this is a lower bound. Let me just try to look at the proof here. So let's do a proof here. And if you do, I'm going to do L2. I'm going to do L2. I want to prove the L2 norm if it's not a piecewise linear function, in the L2 for the quarter uniform grid, it's going to be bounded by C to the H square for the quarter uniform. The way to do is you write the U, if VH is linear, you do piecewise L2 norm. This should be a semi-norm, by the way, that's a typo there. So you can, this way should be 0. Then you do a quadratic interpolation, do a triangle inequality. For quadratic, you can have a 2 plus delta, maybe H delta. This one you do a inverse inequality, and you keep the first term. This one you do a triangle inequality again. And for this quadratic interpolation, you have H negative H2 plus 2 plus delta. Yeah, because it's quadratic. And this one uses inverse inequality. So you notice that these two terms are about the same. So this one is the L2 norm. So you kick this term back. You kick this term back. As you can see that if H is sufficiently small, if this one is, if H is sufficient, it's going to be smaller than this one. So you get this lower bound. I was very happy, this is actually a very simple argument. But anyway, if it tends into the finite element in terms of, we're talking about a quasi-uniform grid, okay? So you get this lower bound. As you can see from the proof, what kind of assumption you want to make. But anyway, so now if you want to compare to this finite, let me show you what I did earlier. So this is my piecewise polynomial degree K. You have this result, okay? This is my neural network. And you can we also prove it's lower bound, okay? With the logarithm, to prove the lower bound, we actually have to use the results I just explained. If we put all this together, you'll find that I'm kind of have a crisis of notation here. I just suppose this is a finite element of piecewise polynomial degree K in RD with all of n parameters. This neural network is the same. If we put them together, if the neural network, if you take any norm, H, L2, H1, H2, doesn't matter. If you take the best approximation, is this power better than the finite element? If these 10, if these 3, you have to, I don't know, you have to do the third order power. So there is much higher order rate of convergence. I still find this is kind of unbelievable, but anyway. So I wrote recently several papers on these things. And again, I did what I call, I actually give a name to this one. I don't know if I'm going to keep it. I call it finite neural method for this one. And I just published it a couple of months ago, I think. The Jonathan Sager and I wrote a number of papers. And especially this one is on this one is archive. This one is on archive, I think. Is that on? This one we're still working on. It's very interesting, actually. There's lots of mathematical questions here that need to be resolved. We explain a few here. So I think about time. How I'm doing here?
Well, you have 2 minutes, 5 minutes if you want.
Okay, okay. So anyway, it has been my obsession in the last 10 years, trying to, just for theoretical curiosity, to do a high order finite element. So the conforming elements method is still open. And but we were able to do a non-conforming, and with the lowest order, we have a universal construction. But m greater than d is not possible to do that. But we have to what I call what I said, minimal stabilization. I believe it is minimal, but I don't. Can I prove it? It's minimal. It's used in Dogana, this interior penalty type of method in the old days. But these days in DG is common practice. So, oh, okay, sorry. Now, somehow I probably, we're talking about this grid, what I call a gridless method. And you have reduced to the power, you have, for example, this one, you have piecewise polynomial of degree n. It's HM conforming with not only good approximation, it's actually super approximation. And I have the theoretical advantage of finite element spectral method in some sense. It's a very high order. It's higher order in the sense that it's a d power higher than the corresponding finite element. Again, my notation is a little bit different. And it's a gridless. Actually, if you want to talk about gridless, a meshless method, you actually have some points, vertex. I was actually joking. This is when it's actually pointless. You don't have any point. It's totally points or vertexless. Grid-free method. It all sounds so good, but there's always a catch. There's no free lunch. You need to solve these optimization problems. Again, I'm sorry, I have different notation here, but it's the same VHK, okay? You need to solve this highly nonlinear, highly non-convex. And optimization algorithm in machine learning is called a training algorithm. This is for me, I don't know how to solve it efficiently right now. So what I've been talking about is just theoretical practice right now. This is a lot of debate these days whether machine learning neural network can be used to solve PDEs, but in theory it looks very nice. And but in practice, you know, it's a ongoing work. For me, it's very interesting because I'm a multi-grid guy. Maybe I can have some multi-grid algorithm that can solve this very efficient. Before that, efficient algorithm is invented to solve this minimization problems. It is still remain to see whether this, what I call a finite neural method or neural network method, would be viable approach for numerical PD. But except one thing which I need to emphasize, it's been widely believed, maybe some theoretical justification, for high order partial differential equation, like I solve shooting equation or stuff like that. And because of the approximation property is independent of the dimension somehow, this cursive dimension at least is not that severe serious in this neural network. And again, it's wide open area, and it is widely believed that neural network will be good for at least for high dimension problem. Here I do a high order PDEs. It's just because something I worked on in the last 10 years, I didn't know how to do it. But this one I have an easy solution. I can prove all this convergence rate, except I don't really know how to solve this one efficiently. With that note, I stop here. Thank you very much for your attention.
Okay, thank you very much, Jinchao. So we have time for questions, sir.